Hello everyone, in this video we'll be going over Activity 11, which is a review of Chapter 18, Electrophilic Aromatic Substitution. Number 1, predict the product and provide a reasonable mechanism for the following transformations. In Part A, we have a benzene ring with an isopropyl group undergoing a Friedel-Crafts alkylation reaction. For an alkylation to occur, the alkyl halide acts as the electrophile and the AlCl3 acts as the Lewis acid catalyst. Cl acts as the nucleophile and attacks the Al and AlCl3 to give us this. Cl is positively charged, Al is negatively charged, and this group acts as a leaving group. So this is loss of leaving group, and that would give us a primary carbocation. But remember how the most stable carbocation is a tertiary carbocation. So that means that a methyl shift will need to occur to give this. And this carbon is positively charged and now is ready to be added onto the ring. To determine which position this group will be added, we need to look at this isopropyl group. This isopropyl group is a weak activator, which means that it is ortho and para directing. So these electrons act as a nucleophile and attack this carbon to add here in the para position. The bond between the Cl and AlCl3 takes the hydrogen, and this is positively charged. This carbon is positively charged. And the hydrogen donates its electrons to make a double bond in a process called proton transfer. And then this is your final product. Part B is similar to Part A in that it has the same reactant, however it undergoes Friedel-Crafts acylation instead of a Friedel-Crafts alkylation. In acylation, the active electrophile is an acylium ion, which is later created, and the Lewis acid catalyst is AlCl3. Chlorine acts as a nucleophile and attacks AlCl3 and gives this. Cl is positively charged, Al is negatively charged, and this group acts as a leaving group. Oxygen donates its electrons to make a triple bond. This molecule participates in resonance, and its oxygen is positively charged. It donates one of its bonds to the oxygen to create this. Now this is ready to be added onto the aromatic ring. As we've seen before, the isopropyl group is a weak activator, which means that it will add in the para position. So this bond acts as a nucleophile and attacks the carbon, positively charged carbon, to add in the para position. The bond between Cl-AlCl3 takes the hydrogen. The hydrogen donates its electrons to create a double bond in a process called proton transfer and gives our final product. Number 2. Which of the following will not undergo a Friedel-Crafts acylation-alkylation reaction? You may select more than one. So we need to remember that a benzene ring deactivated by a strong electron withdrawing group is not electron rich enough to undergo a Friedel-Crafts reaction. So this means that both moderately and strongly deactivated rings cannot undergo Friedel-Crafts reactions. The first ring is a strong activator, which means that it will undergo Friedel-Crafts reactions. The second ring is a strong deactivator, which means that it will not undergo a Friedel-Crafts reaction. The third ring, bromine, is a weak deactivator, while this group is a moderate activator. Since neither of them are strongly or moderately deactivating, then that means that this ring will undergo a Friedel-Crafts reaction. NO2 is a strong deactivator, which means that it will not undergo a Friedel-Crafts reaction, and NH2 is a strong activator, which means that it will undergo a Friedel-Crafts reaction. Number 3. When NN-dimethylaniline is subjected to bromination conditions, ortho and para products are observed. However, when NN-dimethylaniline is subjected to nitration conditions, only the meta products are observed. Explain. So under bromination, the lone pair on the nitrogen makes the substituent an activating group, which is why the Br adds in the ortho and para position. In acidic conditions, however, the nitrogen is protonated, which means that the lone pair that would have activated this group has disappeared. Instead, this has become a positively charged group that withdraws electrons, resulting in a deactivating substituent, adding the NO2 in the meta position. Number 4, complete the table by filling in the boxes with the appropriate starting material, reagent, or product. The first benzene ring undergoes a bromination, which adds a bromine group. And then magnesium and then acetone, which looks like this. The magnesium adds on the bromine and acts as a leaving group, and allows the acetone to add like that. The next benzene ring undergoes a Friedel-Crafts alkylation reaction and adds a methyl group. Now the next substituent to be added is an NO2. The methyl group is a weak activator, so one would think that the NO2 adds in the pair position. However, toluene reacts much faster than benzene, as the CH3 group is electron donating, which makes the ring a better nucleophile. But when you compare the relative stability of the sigma complex intermediates, you'll see that the ortho attack is much more favored than the meta or para, because it is a more stable sigma complex intermediate. So that means that the NO2 adds in the ortho position. Excess NBS will add a Br3 group onto the methyl group. This molecule is brominated to create this molecule, but understanding the difference between these substituent is really important to understand where the bromine adds. So this substituent is a weak activator, while this is a moderate activator, and since this is the stronger activator, this is the priority, so it's going to add para from this ether group. So we'll add the Br2 with the Lewis acid catalyst, and then next thing that we need to do is add a magnesium, so that acts as a leaving group, and then we'll add a epoxide to receive this molecule. Number 5, synthesize the following targets from benzene. Be mindful that Friedel-Crafts reactions cannot occur on moderately or strongly deactivated systems. Part A, we have 2 deactivating meta-directing groups, and notice that we can't add a carboxylic acid group directly onto the benzene ring. However, a way that we can do that is add a methyl group, follow that with the Jones reagent to create the carboxylic acid group. And since this is a moderate deactivator and this is a strong deactivator, they will not undergo a Friedel-Crafts reaction, so that means that the Friedel-Crafts reaction has to occur first. Now that we've added the methyl group, we need to convert that to the carboxylic acid. Notice that we're using the Jones reagent before the NO2, because if we add the NO2 right now after this weak activator, then it would add in the para position. We need it in the meta position. Carboxylic acid is a moderate deactivator, so it will add the HNO3, the NO2 group in the meta position. Part B. So in order to get the NH2 group on this molecule, you'll need to first add NO2, and follow that by either zinc or iron, HCl, and NaOH to give NH2. However, you'll notice that NH2 is a strong activating group and would put a chlorine atom in its pair position, which is not the case in this situation, so we'll have to work around that. First, we'll add the HNO3, H2SO4, which will give the NO2 group. And then the chlorine, since we want that in the meta position. And then finally, zinc, HCl, and NaOH to convert the NO2 group into NH2. Part C. So notice in this molecule we have a strong deactivating group, and remember that strong deactivated rings will not undergo Friedel-Crafts alkylation or acylation, in this case alkylation. So that tells us automatically that we need to put the Friedel-Crafts alkylation before the rest of the substituents. Now the next substituent to be added would be the NO2, because it is directly under or in the pair position of the alkyl group. And next, we could either add bromine or chlorine first or second. It doesn't matter because both are going in the ortho position from the alkyl group and the meta position from the NO2 group. But also remember that strong deactivating groups cannot undergo Friedel-Crafts reactions, but don't get confused with the bromination and chlorination. And that's the final product. Part D. Notice that we have a strongly deactivating substituent and a moderately deactivating substituent. But also notice that this moderately deactivating substituent can be added through Friedel-Crafts acylation. So this is the first substituent to add. And it isn't chlorine because chlorine is a weak deactivator, which means that it's ortho-para directing. But neither of these substituents are ortho or para to chlorine. So the first step is the Friedel-Crafts acylation. Next is the NO2 group. Notice that we did not add the Cl, because if we were to add the Cl instead of the NO2, then the next substituent to add would add in the ortho or para position from Cl, which isn't the case since all substituents are in the meta position from each other. part E is really similar to part D, except that it has one more substituent, a weak activator. And you'll notice that these two substituents can be added through Fiedel-Crafts reactions. And that automatically tells us that they occur before the NO2, which is a strongly deactivating group. Now, to determine which Friedel-Crafts reaction occurs first, we'll see that if we add the acylation, then the alkylation group has to add in the meta position, but it's not in the meta position. The acylation group is para from the alkylation group, so that tells us that the alkylation group has to occur first. And then the acylation, Friedel-Crafts acylation group. And then the NO2 group. Notice that we didn't add the Cl before the NO2 because the Cl is a weak deactivator and would add in the orthopara position, which isn't the case. Number 6. Criteria for nucleophilic aromatic substitution. Number 1. The ring contains a strong electron withdrawing group. Number 2. The ring contains a good leaving group. Number 3. The leaving group is ortho or para to the electron withdrawing group. So A, predict the product of the following reactions. We'll see in this molecule that we have a good leaving group, the Cl. So that checks that off. And NO2 is a strong electron withdrawing group, so that checks that off. And the leaving group and the electron withdrawing group are para to each other, so that checks that off. And this is a strong nucleophile, so the reaction would occur as such. In this molecule, we have a good leaving group, but we do not have a strong electron withdrawing group, so there is no reaction. Part B. Propose a mechanism for the following reaction. An electron pair on the oxygen attacks the carbon with the Cl group, or the leaving group. The electrons from this double bond move to the carbon to create this. Now this participates in resonance to stabilize this intermediate, and these electrons make a double bond. These electrons make a double bond between C and N, and the electrons from this double bond are moved to the oxygen. Now these electrons make a double bond between N and O. These electrons make a double bond here, and these electrons make a double bond here, forcing the leaving group to leave, creating this final product. Number 7. Synthesize the following targets from benzene. Provide all major intermediates along your synthetic pathway. So starting from benzene, this molecule will undergo Friedel-Crafts acylation. Then followed by bromination, notice that this is a moderate deactivator, which means that the bromine will add in the meta position. Then followed by MgBr, CH3, and H2O to receive this substituent group. Notice that we didn't start with bromination because bromination is a bromine is a weak deactivator, which means that it is ortho-para-directing, but as you can see, the substituent is in the meta position. So that means that the Friedel-Crafts acylation has to occur first and then transformed into this substituent group. In part B, notice that these two substituents are para from each other, and Cl is a weak deactivator, which is ortho-para-directing. So we'll start off with chlorination. Then Friedel-Crafts alkylation. But notice that we need an alkene, and this is an alkane. So in order to convert the alkane to an alkene, we're going to use NBS in radical bromination to add a bromine atom The next step we need to do is turn that into a double bond, and the way you can do that is by adding NaOH. And that's your final product.